Well, while the bowl was somewhat repairable by glue, the image here was taken, or the image there was taken after it was glued back together. I created a piece that was not repairable in that same way, at least. Exactly the same glass, same company, same mismarked COE, and all of the lighter colored glass on top, you can see the colors in it, are all dichroic glasses, and they were all supposed to be the same coefficient of expansion of the other glass that I was using. Well, it turns out it was there were several pieces in there, and we later figured out which one it was just by looking at all the various pieces that did actually break. It was a specific dichroic piece, and so what I did here was I slumped it back I slumped it over a specific waveform. I slumped another piece of iridized glass and then glued that glass on it and over the boundaries to break it up a little bit to make it more artistic. Used these metal rods, these threaded metal rods, to make a frame out of it. It was after all an engineering firm, a military engineering firm that made a lot of equipment and test equipment for the military, and glued it back together and hung it up. I liked the way it looked, but this was a piece that blew up and was irreparable. The only thing you could do is melt it back down and hope the next piece that it became didn't break, or glue it together like I did here. Okay, so what happens to glass like this can happen to electrical components. And in electrical components, there are two eventual outcomes. One, it starts an electrical fire, or two, it simply explodes like this glass did. And the difference is according to the specific weaknesses of the system and the current going through it, how it oxidized, the air conditions, is there salt in the air, was it oxidizing more? There's lots of factors in there you don't have to worry about. You don't have to know that. You just have to find those problems and identify them, so you don't have an expansive problem like we had with this glass, where you might have a piece of equipment blowing up. In a mechanical system, slightly different forces can cause even worse results. If a powerful motor or engine seizes because of excess heat, destroying the bearings or the various components of the engine, you could have quite a catastrophic event, quite a catastrophic explosion. People can die in these events. This is serious business. Here, just as with the aquarium or the glass, or with the AUTEC infrared services, now the air syndicate, the thermodynamics are critical to understand. And yes, you can put the pieces back together again, but this is expensive, and like most thermodynamic processes, they are not reversible. A ship fire can cost the upwards of $500 million to repair. Yes, it is costly to have too much heat in the wrong spot. We have discussed at one point or another all three of these methods of heat transfer. Conduction, where the heat travels via vibrational energy through the physical mass, that is, the ability of the mass to transmit energy by physical contact, by vibrating the molecules themselves around it. Or convection, like in the oceans or inside the earth or the sunspots, your oven at home or in the cloud that we saw. The fluid convects according to their specific heat and therefore their density. And lastly, radiation is what you will be looking at as a thermal imaging expert, and energy reaching the surface and some percent of that emitting to you as infrared light seen by the imaging device itself, translated to the colors that you see on the screen and available for analysis by the thermographer. What then is the bailiwick, the sphere of expertise and influence of the certified thermographer? The range is growing as new applications arise. Not shown here are fields friends have worked in, including electronic designs where you're studying heat flows inside of a circuit or inside of a box that's holding a circuit, such as a computer box. You have to design those so the airflows carry the heat away from the computer itself. The processors get warm. They need to lose that heat. That's where you have fans. But even in secret aircraft, while they're being designed, of course you have to have the appropriate clearances for that, but the field grows. Pictures here, clockwise from the left, a motor driving a pump on a ship, a geothermal desalination device at SDSU. That was my project. My wife patiently waiting for me to complete the job. Actually, I broke the circuit. We're going left to right, top to bottom. And where actual human and animal medical imaging is now being done, in some cases preferred to other kinds of imaging, because it's not invasive. It's only seeing things that are coming out. They don't enter you, they don't pass into you, they don't cut into you. So it's non-invasive, as this is. It's non-invasive, non-destructive. And then finally, the electrical systems for preventive maintenance and predictive maintenance programs. All of industry needs these at one level or another, and all should be doing them. They would save money and time and replacement cost, and that can be quite costly. In our second module, we will discuss thermodynamics with more emphasis on the electromechanical thermal imaging field itself.